Hi guys, can I get a sound check? Okay, great, thanks. Oops. All right, guys, how you doing? I hope everybody's doing good. I was gonna do like I haven't done one of my. So I was harping you guys on the Wall Street Journal front. So I thought I would talk to you guys about a little something else that was on my brain, business-wise. So is the idea of I'm looking at starting a new company. So we've got like putting the paperwork through, etc. So I don't know if some of you guys are interested in doing entrepreneurial things or whatnot, or doesn't really matter regardless. I think one of the things that I was pretty aware of from the get-go in my career, but I've noticed a lot of people aren't necessarily, a lot of engineers, is your ownership or potential ownership in the company you work for. And so you can, there's definitely, whether you're starting a company or, you're part of a company, your compensation is like your salary, your benefits, but then a lot of companies, a lot of private companies, public companies, private companies, whatever, people actually have ownership in the company. Okay, so like any company you go work at, that let's say it's like even if there's like Apple and Google and NVIDIA and these kind of places, they actually give you stock options. And that's what I wanted to talk to you guys about. Or, you go, the company that bought my business is a more traditional company. And they don't give stock options to most of their engineers, unfortunately. Those guys didn't. But I was an executive the way, they bought us, and I became like a VP level person, etc. So I would get stock options. So there's always, at the company, there's always ownership. It just depends on how deep it goes into the company. Does when you're a startup, when you're a small company, like at our company, the way it was, all the engineers had ownership in the company. The receptionist had ownership in the company. There's a different percentage of ownerships. So how does this work? Okay, so there's essentially there's a bunch of different company structures that that exist. The two main ones for technology companies or for a lot of companies, or and I'm not a lawyer, guys. I'm just telling you guys from what I know as a person who's set up a few different companies, etc. So you have two major types of companies. One is called a C corporation. And that's kind of like the typical corporation you can think of. You know, most public companies are like this. They have to be. Or I'm just going to call all, I think it's basically all public companies. Or C corporations. And then you have limited liability corporations are also very usable. Okay, so C corporations, so LLCs, limited liability corporations, have like owners. And so you own a percentage of the company. And I hope I'm not telling you guys, but it's like, you know, maybe I think there's a limit to how many owners they can be. Maybe I think it's up to 50 owners. And you might want to set up your company like this. It won't be like a public company because notice it's limited to only 50 people. If you're a public company, you want to have shares, you want to have like everybody in the world buying your shares. So you can't just be limited to 50 owners. You might have hundreds of thousands of owners. Everybody who owns a share of a C corporation is an owner. So certainly all public companies are going to be C corps. But this one has a limited number of owners, but there's some interesting tax things that your income goes directly, you know, it doesn't get taxed here at the corporate level. It basically, the income flows to the owners and gets taxed at the owner level. So some people, for some things, or for some people, it's more beneficial. Sorry, guys, my dogs. I have some guest dogs here, so they might be acting up. So I think most of what I want to talk about today is related to C corporations, where you guys might end up working at or building those companies, God willing, somewhere down the line. So the way the C corps work is they have shares. So it's not percentage ownership, but there's a certain number of shares of the company. So they've taken the ownership of the entire company and divided into, 1 million shares or 10 million shares or 100 million, whatever shares, they can do any number of shares. And each one of those shares, let's say if you have a $1 billion company, you could have a 1 million shares, each one's $1,000, right? So, your grandma could own one of those shares, you could own, 10 shares. The guy who started the company, maybe he owns like 100,000 shares or something of those. But those are what the shares are of the company. Okay, so as an employee, the company has the ability to give you stock options, which is how companies usually give ownership to their employees. And these are divided into, there's a couple of different stock options. There's ISO and there's non-qualified. Stock options, I think. So what an option is it's just a really great deal. The reason it's called an option is the company's giving you the option of buying a share at a set value at a specified future time. Okay, so let's say the share of whatever company, let's say go work in a company X and their shares are in 2021, their share is $100. Okay, so they give you 1,000. This would be a pretty nice deal. It would give you 1,000 options. Well, it may not be such a small, nice deal. 1,000 options priced at, let's say it's priced at $90. That's it, they're priced at $100 each. And these can become due. Usually the vesting happens on a 4-year schedule. So it means that each year you can buy a quarter of these options. So in 2022, you can buy 250 of these options. 2023, you can buy another 250 and so on. Okay, so each time you buy it, you'd be buying it at 250, say, or times $100 per share. Okay, now you don't have to buy it. You have the ability to buy it, but let's say it comes out to 2024. At that point, the stock is worth $200 on the stock market. So now you have the option. So in 2024, you vested all your shares. So you have the option of buying 1,000 shares at $100. So you can spend $100,000. But those shares are now worth on the open market at $200,000. So it's as if you got an extra $100,000 at the end of 4 years. Okay. Now, let's say the shares didn't go up or they actually went down. Well, you don't have to buy those shares if they went down. You have the option of buying them. That's what makes it, the whole business, such a good deal, is it's not forcing you into anything. It's just, saying if the company valuation goes up, you'll share on the upside. If the company valuation goes down, you don't lose anything on the downside because you don't have to buy those shares. Okay, so these options are really valuable. I just find like a lot of the younger engineers, or you see this in biotech, a lot of places where there's a possibility of getting options. Some companies have them, some don't. It just seems like a lot of people aren't like aware of them or don't realize the amount of value you can get for these options, and they just don't even look at them. But I really strongly suggest you guys to look at, when you're going to join a company, to see if, one, this is part of the compensation. If it's not, at what level becomes part of the compensation. You want to go to a company that it is part of the compensation, all those kind of things. So, but having ownership in a company doesn't mean that you just build a company, or that you have to be the CEO or whatever. Again, a lot of high-tech companies are, the ownership spread pretty well down, especially in the technical teams, because they want to motivate their engineers. They want to give, from a business owner standpoint, what your benefit to you is. You want everybody to act in your company as if they're an owner and not just an employee. It's just, you get a different level of contribution from people that way. So it's just a great scenario, again, for, I believe, for people who start the business, for the management as well as the employees. But it's something you have to be to be cognizant of and look at. And the numbers can add up. If you've got either a startup or a small company that can grow rapidly potentially, or if you have a high-flying company like in the chip design business, like you could use the example of NVIDIA or somebody like that. It could be some reasonable amount of money. You never know. It depends on the stock market, depends on how well the company's doing, and etc. But at a place like NVIDIA, I heard if you were sort of a senior designer, not I'm not talking about VP level, direct level, if you're just like an individual contributor, senior chip designer, in just your stock options every 4 years, you could sort of expect to get like an additional $1 million in compensation. So it can be pretty reasonably significant. In like, again, it depends on how well the business does and what percentage of the business you own. But in my own life, I've had pretty good success. I started one company myself, so I had quite a bit of shareholdings there. But previous to that, I'd worked in another company, and I was an engineer, and I made enough to pay for the down payment of my house over here, which is nice. So anyway, just something to think about. Any questions about that, guys? If you really want to dig into the details, which I suggest you do, and I suggest when you guys go and find out where you want to work, do find out if that's option, those are possible or not. But a book to get, if you really want to get into the details, it's called Consider Your Options. I forgot the name of the author. It's probably like 20-25 years old, but things really haven't changed that much. But you want to look at this because it does get quite a bit more complicated. There's different types of taxes, short-term, long-term, capital gains tax, short-term capital gains tax, different kind of things, different type of things you have to worry about. So if you want to get into the details, and again, I suggest you do, I suggest as engineers, you get really friendly with your options and really dig deep into the options, because it could be a lot of value to you guys, is really understand them. And it also helps you think about what kind of companies to go work for, with the mindset of ownership. That's really important. If you look at how much value is in the US stock market and technology companies, you want to get a piece of that action as part of your compensation. And a lot of these companies, you get pretty good salaries. It's not like they're like cutting their salaries. It's sort of like an additional thing. Very, very nice feature. Okay, guys. So that was the stock options. Now I'm gonna so going back, we talked about how, we looked at the CMOS logic, what it looked like. We had the model of switches, NMOS and PMOS transistors as switches. And so, we said with those type of simplified models, what happens, and being able to do binary logic. And we talked about that NMOSFETs are good at passing low values, but bad at passing high values, or good at passing binary zero, bad at passing binary 1, vice versa with the PMOS transistors, and so on. So slide deck 5, which I had put up, I think it was a week or two ago, and I sort of put up the lecture recorded to help us catch up, went into the next layer of details of why this is the case and how does a MOS transistor really work. So we went through talking about the actually NMOS transistor has, and we did mostly NMOS transistor, but PMOS is sort of similar, how it's really not a switch. We're pretending it's a switch, but it's really this really sort of very complicated device, 3-terminal transistor, has current voltage characteristics. And we did a derivation of how we get those currents and voltages to first level, stepping through these things, it was sort of like derivations of IV curves and so on, and why things happen. And the sort of the summary of what we what the slides were saying was sort of this summarizes this first level model of the transistor. Basically, it says that if your gate source voltage is less than the threshold voltage, the transistor is off. If for both of these cases, the gate source voltage has to be higher than the threshold voltage. If that happens, then the transistor is on. Depending on the drain source voltage, so once this is the transistor is on now, and now you have to say, okay, is the drain source voltage less than VGS minus VT? If it is, it follows this equation, and it looks like a really crappy resistor on the drain source versus IDS graph. So it looks like kind of a resistor type of thing, because IDS then is dependent on VDS, but in this weird square-ish way. And for each VGS, you'll have like a different curve. And if VDS is larger than this VDSAT value, and for this VDSAT is always given as VGS minus VT, then you get the square law curve, but it has no VDS component, so it just looks like a current source. Okay, so that's kind of like the summary of the slides. And then I'm going to circle back to the capacitance and talk to you guys more about that. So at this point, I was going to go to slide deck 6, assuming that you guys had already seen these videos and gone through these slides and so on. So do you guys have any questions about this? Anything you want me to go over again? Anything that didn't make sense? No? Going once? Going twice? Okay, so if you guys didn't have any questions, again, if you haven't gotten a chance to look at the recording, please do. Hopefully it covers it in some detail. I think I went through the slides. It was like a couple hours, no, an hour and a half, 2 hours or something. So that was good. So let's see. So let's see. Where is? Okay, so it brings us to this guy. So I'm assuming that we are all familiar with. So I'm gonna try to do the heroic. This is like the few things I've memorized, but my brain has turned into mush. So I'm gonna recreate that curve. So if the gate source voltage, so this is all for our MOS.
Professor?
Yeah.
Did you post slide deck 6 yet?
Yeah, did I just stick? What happened to 6? Good question. So what were we looking at? 5? What was slide deck 6?
Yeah, I only see up to 5 here.
Yeah. 6, 6, 6. Good point. Why am I jumping over 6? There's a good reason for it, but I don't know what it is. Hold on a second, guys. That's a very good question. Oh no, sorry guys, the dogs are acting up. Excuse me guys, let me go close the door here so that you get some level of quiet. All right, guys, sorry about that. So let's find slide deck 6. Where is slide deck 6? Maybe I've just mislabeled, is it possible? Sorry, guys. Let me see. Hmm. Mhm. Sorry, guys, almost there here. There's the mysterious slide deck 6. Wow. Actually, slide deck 6 is important. Let me put that up. Thanks for catching that. Let's see. Let's- Wow. Sorry, guys, I'm putting it on canvas. 1 second. Yes. Slide deck 6. Okay. So module. One. There it is. Okay, guys, so it should be coming up here in a second. Hmm. Are you guys seeing it on canvas now?
Yes.
Yeah.
Good. Sorry about that, guys. Sorry, I have to close my. Still not showing up. There it is. Okay. Almost there. Okay. And of course, I managed to close. What? And it says I'm unauthorized. What? Okay, sorry guys. So slide deck 6 is about, slide deck 5 was about the what should I say, sort of first level model of a transistor. So slide deck 6 is all about second order effects, but second order effects that are pretty important and sort of key to what's going on. And it's sort of divided into two areas. One of them is all the second order effects that happen when the transistor is on. So this is, non-ideal transistor behavior or second order effects. Effects. So these are on transistor, off transistor. Okay, so one of the key things that we said about CMOS, that if I look at a CMOS inverter as a representative of the whole family of CMOS logic, looks like this. So I have a CMOS inverter, and this guy's gonna drive one or several other gates. Let's say they're inverters. Again, just to be simple, but they could be other things. That could be NAND gates or whatever it's driving. Generally, it looks like it's driving, if I was going to model all these things, it looks like basically it's modeling or driving a capacitive load. Okay, so it's not driving anything resistive. It's driving all these gates, so it's driving a capacitive load. And that means that, either you're putting current in here to get, this is VDD. So either you're making this point, so this is also known as binary 1 value. So either you're putting VDD on here to making this point high, or a high bit value or whatever, or you're discharging it to ground and making it a binary 0, driving these other gates. And we said that there is no current flowing, except when things are switching momentarily. Both of these guys will be on, as we'll see. But most of the time, you're either charging a pure capacitor or discharging a pure capacitor. Okay. So, and what's important is just basically the current that you're pumping in or out. That current basically sets how fast you're running. So you have a current, so the change in voltage at the output is your drain current over the sort of your load, effective load capacitance. Okay, so, and your, in the previous set of slides in slide deck 5, it basically was implying that I sub D is basically proportional to beta and VGS minus VT. Okay, this was the proportionality. And furthermore, beta was mu Cox W over L. Okay, so basically you had this situation where if you're designing the transistor, you'd want to make the transistor wide to pump a lot of current. Then you want to use a minimum length. So you want to basically have the aspect ratio, the width over length of your transistor to be large, because, you know, relatively large. You don't want to just go crazy and make it huge, because you got to remember something else is driving you. And this W times L is the input capacitance of you yourself as a gate. So if you just made this thing, this W over L, just a huge number unnecessarily, you would slow down the overall system, because you yourself would have a big gate capacitance and would be difficult to drive. But within reason, basically you wanted to make W as wide as possible to get a big current out when this device was on, and minimum length. And then this stuff basically was process related. So as you go to smaller and smaller processes, the mobility typically stays somewhat constant. Although I'm not sure I can say that, but it's usually something you don't think about, mobility. But as you go into the lower and lower nodes, your oxide capacitance gets higher and higher, because your gate capacitance is getting thinner and thinner. The other way you can look at it is you're getting, because your oxide is getting thin, your gate is getting thinner and thinner, you're getting more and more control over your channel from the gate, meaning you're getting more and more current as the gate oxide gets thinner and thinner. So as you're getting into the smaller nodes, you're able to pump more current. So as beta is kind of increasing for the same W over L. The other thing that's happening is, remember, this is dependent on VGS minus VT roughly, this current. Again, it changes depending on you're in linear saturation, but let's say you're kind of related to this. This gate source, again, you're being driven by the previous gate. So the gate source ends up being VDD. Okay, so as your process nodes are going down, your supply voltages are going to go down, and we'll talk about why that is. But so that's losing you some ground. But then your VT is also going, it's also going down with process node. And there's a limit to that. And we'll talk about that as well. So that's what happens in our previous model when you're driving, when the transistors are on. Okay, you're pumping current in, pumping current down. So the second order effects for when the transistor is on is all the things that affect these assumptions. Okay, there are various things that have to do with high electric fields. So, you know, you gotta remember. So you have, like, let's say like a 65 nanometer process. Let's say you have your gate TOX is 30 angstroms. Okay, so it's maybe like 0.3 nanometers. Okay, let's say your supply voltage is 1 volt. Okay, doesn't seem very much, but you got to remember your electric field is your voltage over distance. Okay, so it's this 1 volt over 0.3 nanometers. Now, I don't know what that is, but it's like a huge electric field because the voltages are low, but the distances are really, really short. So you can get really high electric fields in your devices, and they cause problems, basically, the higher electric fields. And then there are other things that affect your threshold voltage. Your threshold voltage is very important, again, because in fact, to first order, there's like a square law dependence here. Okay, so very dependent on this threshold voltage. But it's, again, your threshold voltages have some second order effects that creep into it. Especially, by the way, these second order effects always get worse and worse the lower the technology node. So if you're in a 0.18 micron process, they're not so bad. By the time you get to a 28 nanometer process, they're like starting to get really, really degrade your transistor performance, or getting more important to worry about. So that's the on transistor behavior. Second thing we'll look at is that our assumption that there is no current flowing when the transistor is off. That was a really good assumption, again, going back 20, 25 years ago. But as our process nodes have gotten smaller and smaller, the leakage, there's more and more leakage currents are happening everywhere. So it is no longer a good assumption that the leakage current, the off transistor currents, are completely negligible. And you got to remember one thing. You got to remember that, let's say you have a chip with, I keep using 20 billion gates, okay, whatever, as a number to use. So at any point, only a small part of this chip is in operation, right? They've designed this chip, this microprocessor. It's got a lot of different capabilities, but at any point in time, they're only using a small percentage of this chip. So let's, for the sake of discussion, let's say 10% of this chip is operating, of the chip is switching at any one time. That leaves like 90% of the chip that is supposed to be off. But that's a lot of transistors. 90% of 20 billion gates is, what is it? 18 billion gates. So even if each one of those gates does like a leakage current in the, nanoamps or some other small number, they'll, you multiply it by, you multiply a small current by a big number in terms of the number of gates or transistors, and it will add up to a significant number. So these days, what you're seeing is that that just a leakage current is, might be as much as 20% of the operating current. That means if you stop the chip completely operating, there'll still be a significant power consumption because of these second order effects. And then you got to do, more and more, set of different things, as we'll see at the system level, usually, to get it to a reasonable level. Sophia, I see you got a note I didn't notice about putting up the annotated slides. Can you email me later? Just remind me to do that. I'll be happy to do that. Just keep forgetting to do it. Okay, so that's what we're going to be talking about. So again, this is the first level model that we looked at in slide deck 5. If the gate source is less than threshold, it's off, and then if you're on, so both of these are assuming that VGS is larger than VT, so on transistor. This is a off transistor. Okay, so assuming the transistor is on, then you basically look at the drain source and decide what kind of current behavior you have. Okay, and it looks kind of like this. If I draw the VDS versus IDS curves, what happens is I will get for each VGS, I get a different curve. It kind of looks like that set of curves. So this is VGS1, VGS2, VGS3, etc. So that's the first level model. And what happens here, for example, in our basic model, this is like pretty important. Notice in our first level model, when you are saturated, it's a straight flat line. There's no mention of VDS here. So no VDS in saturation, meaning flat IDS versus VDS. So I should have been more careful, I guess, to draw these lines, but this would be just a completely flat line. Okay. And then you also have a square law dependence on VGS minus VT, which means these jumps are pretty big. But if this might be true and truer in a 0.18 micron process, but as you go lower, so for example, this is a 65 nanometer process, which is already like fairly old. It's maybe 15 years old or something, 10, 15 years old. And if you look at the actual VDS versus IDS curves, so this type process, this maximum supply voltage is 1 volt. You'll see a couple of non-idealities. Okay, so these black curves are the ideal curves calculated. So you see two things in a plot like this. One of them is that these IDS versus VDS curves are not flat out here. There is a curve, or not a curve, a slope to this thing. The slope isn't 0. So there is a dependence of IDS even in saturation on VDS. And this is by an effect called channel length modulation, and we'll see that. Okay, so that is one thing, that one big difference. So that our equation that says in saturation, this is equal to beta over 2 VGS minus VT squared. This is sort of, I should put this in light, isn't true anymore. Exactly. The second thing, which also affects this equation, is that this is VGS of 0.4 volts. Okay, it's pretty close to the same curve. VGS of 0.6 is kind of close, but as the gate source voltage goes up, you'll see the transistor, the current doesn't go up as much as you would hope. And in fact, at a VGS of 1 volt, we are getting about, I don't know, this is like maybe well, I should know. This is, what is this? No, I guess I don't know. Maybe 0.6x the current you would expect with our simple model, right? This curve, even with the slope, should have been out here, but instead it's down here. So it doesn't have as much of a jump in current. It's a pretty good close match here, in the lower VGS voltages, but as you crank up the VGS voltage, you don't get as much current as you hope. So this square law model is also, it's another way this isn't working. So there's some VDS dependence here in reality, and the square law isn't really working. Okay, so those are the major differences between the second order effects and our level 1 models. Then when you look at the off current, so that's the on current, like it has this kind of curve. So the same process, when you look at the off current, so this is a low voltage process. So again, VDD is 1 volt. And the threshold voltage is also pretty low. So the threshold voltage is, and it looks like maybe it's around 0.3 volts. And our model says that our drain source current should go to 0. So if our threshold voltage is 0.3 volts, if our VGS is less than 0.3, we should be at absolute 0 for our drain source current. But in fact, what you see is, so what it should look like if it was doing that, it should be doing something like get to the threshold voltage. So this is IDS versus VGS. Okay, so it should get to VGS and go to 0, wherever 0 is. But instead, when it goes below the threshold, there is still current. Notice it's dropping pretty fast. This is a log scale. It's not a linear scale. So it's dropping pretty fast, but it's still not 0. So by the time you get to VGS of 0, this is when the transistor, this is like a binary 0 being at the gate of the transistor, meaning that the transistor shouldn't be switching at this point at all. You still have a significant current. You still have a significant off or leakage current. And this is 27 nanoamps per micron of gate width, which is quite a bit. I mean, like each gate might at least be 1 micron of width, say. And imagine if you have like, I don't know, let's do a quick calculation. Let's say if you had 1 billion transistors, 1 billion is 10 to the 9th times 27 nanoamps. Let's say each one of those billion transistors had this much current. So that would be like a humongous current. It would be 27 amps of leakage current, with just the device sitting there. And on a 1 volt supply, so power consumption is IV. So it'd be 27 amps times 1 volt is equal to 27 watts. So that chip would just be sitting there sucking up 27 watts, even when it's not doing anything. Imagine your phone using up 27 watts when it's like basically off and you're not making phone calls, just sitting in your pocket. It just wouldn't stay charged for very long. So anyway, you got to do something about it, but this is how these transistors, these advanced processes are now working. Okay, so let's look at first thing is like the effects of a on device. So we said that the second order effects when the device is on, there's a dependence on electric field effects. Okay, so there's 2 types of electric fields when you look at a gate. So if I draw the transistor, this is the silicon dioxide, that's the gate. This is the poly. This is where you apply the VGS. Assuming this is the source, is N plus. So let's say this is grounded, and this is grounded. So you have, and then there's some, this is sort of the output, right? So this will vary. So there's two kinds of electric fields here. One of them is what's called the vertical electric field. So that's these electric fields that are going in this direction. Okay, so if you look at these electric fields, because it's going in this direction, it's basically this VGS voltage divided by the thickness of this oxide. So these electric fields are roughly, again, as VGS divided by thickness of the oxide. Okay, so those are electric fields. Just when the device is operating, you have these electric fields like this, and they are pulling like electrons towards the surface. Okay, and pushing holes away from the surface in an NMOS. Okay. And then you have the lateral electric fields. The lateral electric fields are pointing in this direction. So they're along the length of the channel. And these depend on the drain source voltage. So this basically depends on this voltage, and this is the transistor length. So this is L. So this depends on VDS over L. Okay. So okay. So what do? So in the long channel approximation, so again, going back to slide deck 5, the effect of this vertical field is it basically is generating and controlling your channel. So meaning that the charge in the channel is dependent or is proportional directly to this electric field in a level 1 model. Okay. And then in the level 1 model, what the lateral field is doing is it's affecting how fast the carriers are going from source to drain. So basically the velocity of the electrons going from the drain to, no, the electrons are going from source to drain is dependent on this lateral electric field by this proportionality constant, which is the mobility. So mu is the mobility of free carriers. So it'd be mu sub n for electrons, mu sub p for holes. Okay, so that's a level 1 model. Okay, but as the electric fields get higher and higher, and remember the reason the electric fields are getting higher, our voltages are shrinking in tighter processes. But what's shrinking even faster are these dimensions. So the thickness of the oxide is going down faster even than the electric field is going down. And the channel lengths are getting smaller and smaller even faster than what the electric field's going down. By the way, this is one of the reasons that they're reducing the supply voltage. Okay, so that's one of the reasons they're reducing supply voltage, because as these dimensions are shrinking, the higher supply voltage would have given us a higher sort of noise headroom or noise margin, but they're just creating really high electric fields. So there's got to be something you're trying to do to reduce these electric fields. Okay, so what do these electric fields do? Then what do they start to do? And so the book has this analogy of a coffee cart analogy. Okay, and I don't know, I guess it's as good as anything. So it basically says that, let's say you are going outside the engineering building at Cal Poly. I don't know if you guys remember even what it looked like. I hardly remember, but like there's a set of glass doors and you're going out, and let's say it's really a windy day. So the wind is, you're trying to go out the door, out to the vending machines or coffee cart or whatever to get a drink. So the wind is the vertical electric field. The wind is sort of, you're trying to walk, went out the door, you're going out, now you're going parallel to the doors or the wall, and the wind is pushing you towards the wall. You have to fight that wind. It's pushing you towards the wall, okay? So that's an example of a vertical electric field slowing you down. It would be something going 90 degrees or perpendicular to your direction of motion, and it's affecting your direction of motion. And then let's say there's a bunch of people walking to get into the building, okay? And you're gonna sort of bump into them, or otherwise you're gonna have to sort of get around them. And those people are also affecting your forward direction. And that's sort of an effect of your mobility degradation and velocity saturation. So those are the analogies to an electron. So let's say an electron is, so let's say with that analogy, say we have our transistor again. And this is the oxide. And let's say you have an electron. So your electron has two second order effects to deal with. One of them is that the electric field is getting higher in the vertical direction. As it's moving from source to drain, it's getting kind of pulled up towards the gate. There's an electric field that's pulling it up as well, so it's slowing it down because it's pushing it towards this interface between the silicon dioxide and silicon. And, at a very fine geometries, if you're really looking at the, atomic scale, this is a rough surface. Again, at like an atomic scale. By rough, we're talking about angstroms of roughness. But as the electron is operating close to the surface, as it's getting pulled by the vertical field as it's moving along, it's getting slowed down, just like a wind would slow you down, pushing you towards the wall of the engineering building. The second thing is, in terms of the lateral electric field, as the electron is moving in this direction, it doesn't happen very often, but it interacts with the silicon lattice itself. As the electric fields are getting higher, you're moving faster, you start basically having interactions with the nucleus of the silicon atoms, etc. And these kind of things are also slowing you down. And that's like people walking the other way, or you're rushing through a crowd. Imagine if that crowd is the silicon atoms and you're the electron, you have to kind of, you get bounced around by that group. You still keep your general direction, but you get to a certain point where you cannot move faster through the atoms, okay? Just because you're not in a vacuum, you're in a silicon crystalline lattice. Okay, so first thing is looking at, the first effect is mobility degradation. Okay, so these are the effects of, what happens when your vertical field is high. So what that does is it slows you down about how fast you can go through the silicon. So you get instead of the mobility, again, remember the mobility, we were saying it's like a constant number. This mobility is, so if you're looking at the velocity of electrons in silicon, in a sort of, electrons would have a certain mobility times the electric field, meaning that if you looked at the velocity versus an electric field, this implies that just your velocity keeps going up the higher the electric field is. But it's not a constant. Okay, it's a complicated electric field, and the upshot is it tends to saturate. Eventually you start flattening out. You get to a certain point and you can't go any faster, no matter how high or much higher your electric field is. And the same thing happens to holes in silicon. Okay, so that's mobility degradation, and that comes from the vertical electric field. So then when the electric field is very high between drain and source, so this is the lateral electric field, the other thing that happens is you also start hitting, you know, electrons, start hitting the atoms, etc. And you also get a reduction in mobility. So you sort of take a hit in two ways. So basically, you know, you stop being able to go any faster. Let's see if I can get this. Okay, so the upshot is between these two effects, basically the higher electric fields are not translating to higher currents, as you would expect, because of this velocity saturation and mobility degradation. Okay, so you don't need to really worry about the exact, you know, the exact equations. I think what you need to remember is the following: that at higher electric fields, the velocity does not just keep going up, but it tends to fall off. And the second thing that you have to remember, which is interesting, is that where the value at which they saturate is higher for the holes than it is for the electrons. That means that, I don't know if you guys will start going back to slide deck 5, we said that I think we said that the mobility of holes, you can assume it's around maybe third the mobility of electrons. So so P MOSFETs have lower, for the same amount of width, P MOSFETs have lower max current than N MOSFETs by a factor of like 2 or 2.5 or something. But as your process technologies shrink further and further, this gets to be less true, and the max current out of a PMOS and an NMOS ends up being sort of close to each other. Okay, so what happens in effect when you do a sum total of all those things, instead of having an equation for your saturation current that is not dependent on, you know, VDS and has a square law dependence, you end up with sort of another type of equation where you have this maximum velocity. Again, this is at the VDD being applied, etc. So you get basically a different current, and you get a complicated dependence on IDS to the supply voltage. Okay, and then there's all this alpha power model and stuff. I don't even know what to do with that. I mean, that's stuff in the book. Honestly, I've never used this stuff in my career, but I think what you have to remember is that the sum of all this stuff is that you end up with, in saturation, you end up with not as much current as you'd hoped. And it's not just in saturation, sorry. So even in linear, so this is less than this, right? So this is what you're hoping for, this is what you're getting. So generally you get less current than what you'd hope for, and also that you do not end up with a flat curve, and you have a slope here on the VDS, VGS curves. And those both affect the transient behavior of your CMOS gates. Okay, because the CMOS gate, when it's on, it's outputting current. You're expecting some ratios between the NMOS and PMOS, and some type of behavior, as we'll see, it affects all of that. What else do I want to say about this stuff? So that's kind of like the sum total. And then the other thing you need to remember is these kind of effects get worse and worse the smaller the processes you're in. Okay, so that's the VDRs. Second order effects. Okay. Now you have, like, let's talk about the next one. So those were like reducing the current. Now the second type of thing is that, so these were, so far, we were talking about these two, what these two effects do is they are reducing our currents. So I keep convoluting these two together, and I'm sorry, but sort of they're both small channel effects. But the velocity saturation and the mobility degradation, they reduce your total current. The effect that makes your slope go up is so-called channel length modulation. Let's see how that works. So the way the channel length modulation works is in a or MOS device, right? Let's say this is our NMOS device. We are expecting the current to be mu Cox W over L VGS minus VT squared. So that was our ideal model. Okay, but what happens is, in reality, this L does not stay constant. Why doesn't it stay constant? Well, it's because this drain is, an N plus dopant or N plus doped region in a P substrate. So there is a depletion region. So it looks kind of like a diode here, except everywhere except right at the channel, but even here, it looks like a PN junction here, right? As far as the substrate is concerned, it looks like that. So this is drain. This is the substrate. The substrate is at ground. So that's a substrate. So this is grounded. And the drain is at some higher voltage, right? It might be initially when the output is 0, it would be 0. When the output is a binary 1, it might be a VDD. Okay, so by the time you get to the VDD, this ends up being a pretty, like a higher reverse bias diode. It's always a reverse bias diode, whether it's the drain is at 0 or it's VDD. But when it's at VDD, when the drain is at VDD, it's more reverse bias than when it was at 0. Meaning that this depletion region and around this PN junction gets bigger. This depletion region gets bigger, takes more space. So it's as if my length starts getting smaller, because the reach, if you can want to think of it that way, the reach of the drain, as the voltage is going up, goes higher and higher into the channel. So it looks like my length is shrinking as my drain voltage is going up. So it looks like I have an effective channel length that's less than the drawn length. Okay, and so a shorter effective length gives you a higher current, which means IDS increases with VDS, even in saturation. So this is the effect that causes this slope increase. Whoops. It causes this slope increase. Okay, so as VDS is increasing, As VDS is going up, this effective length of the channel is shrinking and like you're getting more current out. Let's see, anything else? Okay, so let's stop here, guys. We're at 8:14, so I guess we'll start back on the threshold voltage effects when we come back on Tuesday. Any questions?
Could you scroll back up to the last slide that we went over?
This one?
Yeah.
Okay.
Okay. Thank you.
Sure. Any other questions, guys? And Sophia, if you could remember, send me an email to put up the annotated stuff. I'd appreciate it. Okay, thanks, guys. Have a good weekend.